What specific problem does the proposed AI-assisted framework aim to solve in the context of mathematical question generation?
The proposed AI-assisted framework aims to address the challenge of generating difficult and diverse mathematical questions that surpass the limitations of both purely human-generated and synthetic questions produced by large language models, LLMs. Traditional human-generated questions are resource-intensive and not scalable, while LLM-generated questions often lack the necessary complexity and novelty. The framework synergistically combines human expertise with LLM capabilities, allowing for the generation of questions that require the application of multiple distinct mathematical skills, thereby enhancing their difficulty and diversity. By employing a structured pipeline that includes skill extraction, question generation, and rigorous validation, the framework ensures that the resulting questions meet high standards of quality and challenge, ultimately creating a new dataset, math squared, that is significantly harder than existing datasets like math. This approach not only improves the evaluation of mathematical skills, but also introduces innovative perspectives for both AI and human learners.
How does the proposed AI-assisted generation method work? Illustrate the pipeline step by step, detailing the role of both LLMs and human experts.
The proposed AI-assisted generation method for creating difficult math questions follows a structured 5-step pipeline that integrates both large language models, LLMs, and human expertise. 1. Skill pair validation. The process begins by randomly sampling pairs of mathematical skills from a repository. LLMs, such as GPT-4 or Claude, assess the qualitative similarity of these skills, flagging and excluding pairs deemed too similar to ensure the generated questions are sufficiently challenging. 2. Question generation. Next, the LLM generates a question and a brief solution that requires the application of both skills. The model is guided by specific conditions to ensure high-quality outputs, such as requiring a single final answer and avoiding logical inconsistencies. In-context examples of human LLM interactions help the model refine its outputs. 3. Solution attempt. The LLM then attempts to solve the generated question, adopting an adversarial approach to identify potential flaws, such as ambiguity or excessive computation. If issues are found, the model halts further attempts and states the problems, otherwise it completes the solution. 4. Question validation. The generated question and its solution are validated against a fixed rubric consisting of 7 criteria, including clarity, computational tractability, and logical consistency. This step ensures that only questions meeting all criteria are classified as valid. 5. Final solution and revalidation. For questions deemed valid, the LLM resolves the question to obtain a final solution. If the answers are unique, indicating potential ambiguity, the question is discarded. Human experts then review the generated questions, refining them for engagement and quality, ensuring the final dataset is both challenging and novel. This collaborative approach leverages the strengths of LLMs in generating creative questions while relying on human oversight to enhance quality and difficulty, resulting in a robust evaluation framework.
What advantages does the math $² dataset offer compared to existing datasets like math, particularly in terms of question difficulty and diversity?
The math squared dataset offers significant advantages over existing datasets like math, particularly in terms of question difficulty and diversity. By requiring the combination of skills from different subareas of mathematics, math squared generates questions that necessitate out-of-distribution thinking, making them inherently more challenging. For instance, while a model might achieve a success rate of 0.5 on the math dataset, its performance drops to approximately 0.25 on math squared, indicating a substantial increase in difficulty. Additionally, the methodology of using random pairs of skills enhances the diversity of questions, as it encourages the creation of novel problems that are distinct from those in existing datasets. This approach not only results in harder questions, but also fosters a broader range of mathematical concepts being tested, thereby enriching the evaluation landscape for LLMs.
How was the effectiveness of the proposed question generation process validated? Discuss the experimental design, metrics used, and the significance of the results obtained from the validation.
The effectiveness of the proposed question generation process was validated through a structured experimental design that involved generating and verifying 180 difficult questions for the Math Squared dataset. The validation process included a 5-step pipeline: skill pair validation, question generation, solution attempt, question validation against a fixed rubric, and final solution revalidation. The rubric consisted of 7 criteria, such as clarity, computational tractability, and the requirement for a single final answer, ensuring that only high-quality questions were retained. The results showed that all tested models performed significantly worse on Math Squared compared to the original math dataset, with performance drops ranging from 13.42% to 92.91%, indicating that the Math Squared questions required a more complex application of skills. This drop in performance underscores the dataset's increased difficulty and the effectiveness of the proposed method in generating challenging and novel math questions that push the boundaries of existing models.
What were the key findings regarding the performance of various models on the Math $squared dataset, and what implications do these findings have on our understanding of model training and evaluation?
The key findings regarding the performance of various models on the Math Squared dataset indicate a significant drop in performance compared to the original math dataset, with proprietary models like GPT-4 Omni and Claude 3. 5 Sonnet showing declines ranging from 13.42% to 35.45%. Notably, the specialist math model Mammoth 7B exhibited the largest drop at 92.91%. This performance decline suggests that the Math Squared questions, which require the application of distinct skills from different subareas, are inherently more challenging and may be considered out of distribution for models trained primarily on the math dataset. The observed relationship between performance on math and Math Squared, where the performance on Math Squared approximates the square of that on math, implies that models may struggle with compositional generalization when faced with questions that necessitate the integration of multiple skills. These findings highlight the limitations of current model training approaches, particularly the risk of overfitting to specific datasets, and underscore the need for more diverse and challenging evaluation sets to better assess and enhance model capabilities.
What limitations did the authors identify in their approach to generating questions, and how might these constraints affect future applications of the method?
The authors identified several limitations in their approach to generating questions using LLMs. Firstly, the generated questions often exhibited issues such as being too similar to existing questions, containing errors or nonsensical elements, and being overly tedious, which detracted from their engagement value. Additionally, the models sometimes failed to adequately involve the required skills, leading to shallow applications of the mathematical concepts intended to be tested. These constraints could hinder the effectiveness of the generated questions in evaluating true mathematical understanding, as they may not challenge learners or models sufficiently. Furthermore, the reliance on LLMs for question generation could result in a lack of diversity and complexity in the questions, potentially limiting their applicability in varied educational contexts.